Good morning, chemists. It's go time. Okay, so I posted the midterm 2 review session information. It's on your calendar. It's in our midterm preparations module. It's going to be on Monday at 8:05 p.m. So in this room, there is a class in here before then. So just be respectful if you're coming in person. Can get quite loud, so I encourage folks to use Zoom as well so you can have a quieter environment. So the packet is on there, so do download that before coming. The midterm exam resources are posted too on my own page, and the department has their practice exams. So right now you have access to 3 Carmen practice exams made by the department. I'll be honest, I do not look through those, so Dr. Foose makes them, so if there is a mistake, give me some time. Do point it out. Give me some time, and I can look into it. But I don't curate those midterm resources. But I do have 1 paper practice exam right now for your studies and the worked out key. I have another one coming on the way, probably today or tomorrow. I'll post the second paper one. Those ones I write, so I take credit for those ones. So if you find mistakes, do let me know. Okay, so midterm resources, because our midterm is next Wednesday evening. Yes, not in this room, in Hitchcock. Okay, all right. So we will continue on with chapter 17. We left off talking about buffers. So in chapter 17, we're looking at all the weird scenarios that have to do with K, specifically our equilibrium constant for our weak acids and weak bases. So the Henderson-Hasselbalch equation is based upon the idea of, the common ion effect. We saw a demonstration last week of the common ion effect that equilibria is shift if we have both the products and reactants present in the solution at the same time. So, what I mean is in chapter 16, we talked about like HA, our acid, just putting that into solution and that slightly dissociating, slightly ionizing to produce a little bit of the conjugate base, a tiny bit. So in chapter 17, we're saying, well, what if I deliberately put both the acid and its conjugate base in solution at the same time? This is a buffer. So I'm talking about large amounts of the acid and its conjugate base, or we could talk about a weak base and its conjugate acid being a buffer as well. And so with this common ion effect, we can draw out an ice table, which I think we did over here in the previous slide, where we have this minus x plus x term. We have initial concentrations of both the acid and its conjugate base. We get our equilibrium line, we shove it into our Ka expression. And so the nice thing is here, because Ka is so small, these things ionize very little, we can make an approximation where we remove the plus x and minus x from those terms. So essentially, this is how we get the Henderson-Hasselbalch equation, where essentially what it is you take the negative log of the Ka expression. We're making the assumption that the analytical concentrations of the acid and conjugate base that we put into solution are the equilibrium concentrations. That's the approximation that we'll do, and that's how we'll handle all of 1220, all of this chapter. This approximation breaks down for really dilute buffers, but that's outside the scope of this class. You have to consider the self-equilibrium of water as well. So yeah, here's the Henderson-Hasselbalch equation, where you can calculate the pH of a buffer. You can only use this when when you've produced a buffer. So one of the hardest things is identifying, okay, in my solution, do I have a buffer or not? And I might have to do a different calculation there. So how we approach the Henderson-Hasselbalch equation to calculate the pH, take the pKa of the conjugate acid that's in the system, and you take the log of the base concentration over the acid concentration. These can also be in mole amounts as well because they're in the same volume. So here I have the generic, HA, our weak acid, A minus, our conjugate base, but we could also use this equation for like a weak base ammonia system where, our base, something like ammonia, would be on the top, and then the acid component would be the conjugate acid, so NH4+. So it can work that way as well if you have a base system. So, but do make sure you're using pKa of the ammonia system, but you're still doing base over acid. And so we'll do some examples. We did some examples of making buffers. And so the first kind of way that we can make a buffer is putting like mole amounts of the acid and the base part of the buffer. And so that's how we get our base to acid ratio, where you add directly into your beaker HA, your weak acid, and A- directly into your beaker. We just need to do a little bit of manipulation to get the base to acid ratio. And so here in this example, we calculated the millimole amount of HF, the acid, and the millimole amount of the base F-. And then that's how we got our base to acid ratio. See how I left out the volume component because we're dividing by the same volume on both the top and the bottom, so they cancel out. So this is for an acid buffer system. The last place we left off was looking at a base buffer system, but the calculation is exactly the same. You just need to make sure you put appropriately the base over acid ratio and using the appropriate pKa. So I give you pKb for ammonia. We can't put pKb into this Henderson-Hasselbalch equation. We need to convert it to pKa first, but the approach is exactly the same. Get the mole amounts, or in this case, I just give you straight molarities. Here's the base component, there's the acid component. We calculate the pH that way. And then one more right here where we calculate the millimole amounts of the base and the acid form. And again, using pKa of ammonia, that does require, some Kw business within there. All right, so these examples are, I guess, the easiest way to make a buffer, where we add mole amounts of the acid and the base. They go straight into the Henderson-Hasselbalch equation. There's a second way we can make a buffer. Okay, oh, never mind. We need to have one more example. Sorry, this is still type 1, where we're just adding mole amounts of each thing. So let's do this example. So here we have a buffer that has a pH of 4.7, and we made it using acetic acid and sodium acetate. What is the base to acid ratio? So if we look at what's given here, we're given pH. We can calculate pKa since we're given the Ka value. So pKa in this instance, if you take negative log of 1.8 times 10 to the negative 5 is 4.74. So we have pKa, and so we're just calculating, okay, what's inside the logarithm in this case. So it's just a little bit different since I give you the pH. So let's calculate this. So 4.70 equals 4.74 equals, plus log base over acid ratio. So I'm just going to calculate that whole thing inside the ratio or inside the logarithm. All right, so let's see, can I do this math? So negative 0.04 equals log base over acid. How do I get rid of that logarithm? Raise both sides to the 10. Yes, all right. And so when you do that, did I write out the work? That'd be nice if I wrote out the work. Okay, yes, I get that the base over acid ratio equals something like, I have it down there, 0.912. So if you take 10 to the negative 0.04, you get a ratio of 0.912. So let's think about what this means. Since we're setting this equal to a ratio, what I like to do, because I'm very simple-minded, is I have a ratio on one side, so I'll make the other side also a ratio. I'll put it, over 1. So in this case, if we look at this ratio for this buffer, what is more present, base or acid? I hear 50-50. Acid is more present. So again, if you write it as the ratio, what this is essentially saying, if I put it over 1, for every 1 mole of acid that's present, I only have 0.9 moles of base present. Does that make sense? So that means more acid is present in this case. Okay, so that's perfect because we need this number for the next part. How many moles of acetic acid should be added to 500 milliliters of this concentration of sodium acetate to make this exact buffer? So I'm giving you sodium acetate. So what component of the buffer am I giving you? The base part or the acid part? The base part, yeah, we need to recognize that sodium acetate is Na, A minus, right? Where we have A minus present. Acetate is the A minus, the conjugate base form. So there's the base. So using this ratio, like I just said, we already said, oh, there's more acid present. So for every 1 mole of acid that's present, there is 0.912 moles of base present. So if I just figure out how many moles of sodium acetate are present, then I can use that ratio to figure out how much acid do I have to add. So how many moles of base is that? So 0.250 moles of the acid. So A minus, this is the base. This is the base part of our Henderson-Hasselbalch equation. So 0.250 moles of A minus. So this is where I'm going to use the ratio I just calculated. Am I going to put the 0.912 on the top or the bottom of this ratio, of this fraction? So look at the units. 1 mole of A is 0.912 moles of B. So am I going to put the 0.912 on the bottom or the top? So maybe I should be better with my wording here. This is moles of A minus, which is what component? The base part or the acid part? The base part. Yes, it is the base part. Yes. So yeah, we have some A's running amok here. So then when we do that, now I ask you, should I put the 0.9 on the top or the bottom? The bottom, yeah. So 0.912 moles of the base for every 1 mole of the acid. The acid, yes. And so that's how we get that number. So 0.74 moles of the acid HA we should add to this concentration of sodium acetate to make this exact buffer of a pH of 4.70. We could take this one step further on an exam question. It could be like, okay, what mass of HA should I add? How would you get that? Just take the molar mass. Yeah, so just one step further, take the molar mass. All right. Okay, how do we feel about buffers? Okay, these are the easier ones, so just hold my hand and follow me into the dark, and we will look at other ways to make buffers that are a little bit more challenging. They require BCA tables. All right, so how do buffers work? Why are buffers important? So like most living things, like our human bodies, are just big buffer bags. We are big buffer bags where the whole idea is like if you drink a soda is what pH? It's very acidic. Yeah, there's carbonic acid because there's dissolved CO2. There's phosphoric acid. That's why it's tasty. So it's like the idea is like, okay, we drink a soda, but the pH of our body stays relatively the same, that the pH doesn't shoot down once we drink a soda. And that's because our bodies have these buffer systems in them to accommodate small additions of acid or even base, so the pH remains the same. And so the idea is, well, how do buffers resist change in pH? It's because of the common ion effect, that when we have a system that is a buffer, meaning that we have large amounts of the acid and the base present, if we add a small amount of HCl, so acid, to this buffer system, what does Le Chatelier's principle tell us? If we add acid to this system that's already at equilibrium, which way does the equilibrium shift? To the right? No, to the left. Yes, to the left, towards the reactant side, right? We're adding a product. The reaction shifts to the reactant side. So the idea here is when we add acid, what we're essentially doing is just neutralizing a little bit of F minus to make the acid form here. That any H plus we add to the system, this buffer system that's at equilibrium, goes towards neutralizing this HF F minus system. That's what's happening. So instead of, that added H plus directly going into the, negative log H plus concentration to calculate pH, it's going to neutralize the H plus the HF and the F minus system that you already have present. Same thing with the base. When we add a strong base into pure water, which isn't a buffer, that OH minus goes straight into a POH calculation. But when you add base into a buffer system, that base goes into neutralizing your weak acid that's present to make your conjugate base in this form. And so adding small amounts of acid and base only change the relative amounts of acid and base that are present. And what we'll see is small changes in the Henderson-Hasselbalch equation that results in small pH changes. So actually, let me write the Henderson-Hasselbalch. So pH equals pKa plus log base over acid. So if we have a buffer system that has, our acid present, so something like HA and A minus, if we add a little bit of acid, what component of this equation are we changing? We're just changing the base to acid ratio. We're not changing anything else in this equation. So when we just change this base to acid ratio, the pH just changes a little bit. And so we'll do some examples here where you see that. And so that's why we don't see a drastic pH change when we add acid or base, because it's not going, those H plus or OH minus values aren't going straight into the pH calculation. They have to go through the Henderson-Hasselbalch equation first. All right, so there we go. So if we look at this graph, we will do titrations here in a little bit, but titrations are not on midterm 2, FYI, but they will be on midterm 3. The buffer region on this graph is the part where it resists pH change the most. So what this graph is showing is the pH of a weak acid system with added volumes of a strong base like sodium hydroxide. And so what we see here between the regions of 2 milliliters and about 8 milliliters, that's a 6 milliliter base range where the pH changes very, very little. But once we get close to the equivalence point where it's no longer a buffer, we see, huge changes in pH when we add just a small fraction of strong base in this case. So in these regions, these are not buffers, all right, where there's large changes in pH. It's just this kind of flat part of this titration curve. That is the only part that is a buffer. When we think about, and we'll do some calculations here, what's present in your beaker at all of the different the different volumes of this titration curve, this region right here where it's flat is the only region where the acid and its conjugate base are present in large amounts. In all the other regions, we use different calculations to figure out the pH, but thankfully you already know how to do it. We just need to know when to do what calculation at what region, all right? Okay, so, more buffer details. Okay, let's see, what did I wanna say here? Okay, so here's our Henderson-Hasselbalch equation. Mathematically, when will the pH equal the pKa of your buffer system? Mathematically. When this log term is 0, when is that log term 0? When the base to acid ratio is 1. So meaning there is a 1-to-1 ratio of base to acid. So right here, basically halfway to your equivalence point in a titration, all right, where you start with HA and you start to add strong base. At the equivalence point, when you fully neutralize it, all you have present is A minus, where you neutralize it. You've taken all of your acid and converted it to its conjugate base. This is no different than, Chem 1210 when we calculated equivalence points of, titrations. Same idea. So when you deliver that volume, when you have equal mole amounts of your weak acid and your strong base, at the equivalence point, you have all converted your acid to base. So the point that we're focusing on here is the halfway equivalence point. Basically, this is the flattest part of your titration curve. At this region, your base to acid ratio is 1-to-1, where you've only converted half of your acid to the base. And so this point is interesting because this is where your pH is equal to the pKa value. So for example, if our Ka is 1.8 times 10 to the negative 5, so if this was acetic acid, the pKa would be something like 4.74. So the point in which your pH is equal to your pKa is at your halfway equivalence point within this titration curve. And so what's special about this point is because it's the flattest, it's basically the point in your buffer that is most resistant to pH changes, because you have equal amounts of base and acid to do that common ion effect thing. All right, so what did I want to say? Due to common ion effect, your buffer is most resistant to pH change when base is equal to acid. So this is when your pH equals your pKa. That is your flattest part. So when designing buffer systems, you want to choose buffer systems that utilize the most effective part of your pH, your titration curve. So for example, you know, if you wanted to buffer a solution at a pH of 6, then this titration curve, this system would be good, because the flattest part where it's most resistant to pH change is closest to your pKa. You don't want to pick a buffer where, you know, you have to be really, really close to the equivalence point in order to maintain that buffer, because if you add a little too much base, then whoop, your pH is going to skyrocket. So the most effective part of a buffer is about 1 pH unit away from the pKa value. So we want to be operating, you know, if we were designing buffer systems for like biological systems, you want to be as close to the pKa as possible, because that portion of the titration curve is the most resistant to pH changes. We don't want to be operating at the edges. All right. Okay, so those are buffer details. Okay, let's keep going. All right, so in this titration curve, this is a weak acid, and we're adding a strong base. So we see a buffer present. A mixture of a strong acid and a strong base is never a buffer, never. And the reasoning here is because, let's think about that. When we neutralize HCl with sodium hydroxide, so both of those are strong acids and strong bases. When we neutralize it, the salt that is created is NaCl. If this was chapter 16 and I asked you what is the pH of NaCl aqueous, what would you say? It is what? Is it acidic, neutral, or basic? It is neutral, yes. Why is it neutral? Because sodium is the conjugate of a strong base, and Cl minus is the conjugate of a strong acid. NaCl is neutral. And if we think about the other product here, water is also neutral. So we see the products here, they're all neutral. When we do this neutralization reaction, everything is neutral. So we don't have a weak acid or weak base present for the Henderson-Hasselbalch equation. So let's calculate the pH. If we mix 40 milliliters of HCl with 50 milliliters of sodium hydroxide. So this is a neutralization reaction. So BCA tables are back. All right. So we need to figure out how much excess strong acid or strong base is present after this neutralization reaction. It's not that bad. I'm going to show you some tricks to speed things along. So remember how we do BCA tables? What's the unit that we need to be in for a BCA table? Moles, yeah, moles. But I'm going to show you a trick here where let's just stay in millimoles because it's easier. So remember, to get a millimole, you take a milliliter amount and multiply by molarity. So I don't want to do any dividing by 1,000 business because that's just too much work. So if we multiply 40 times 0.1, what's that number? 4. 4 millimoles of HCl is present. How many millimoles of sodium hydroxide are present? So 50 times 0.2. 10? Is that 10? Yes, okay. 10 millimoles of sodium hydroxide. So those are the values that go into our BCA table, but in which line? In the B, C, or A line? B, yes, those are the initial concentrations of the things, and we're going to mix them together. So 4 millimoles of HCl, 10 millimoles of sodium hydroxide. Millimole. So what's our limiting reactant? So something needs to be consumed fully. Which one is it? HCl. So minus 4. Oh, these are zeros. Minus 4. And then how much NaOH is consumed? Minus 4 as well. How much NaCl is produced? Plus 4 and plus 4. Great. So after this neutralization reaction, we have 0 moles of HCl. We have 6 millimoles, of NaOH. And then we have 4 millimoles of NaCl and 4 millimoles of water. Okay, so let's just look at this after line. How would you calculate the pH of this? Think about what's present and how you calculate the pH. Let's think about what we can ignore. You already told me NaCl is aqueous. Salt is what pH? It is neutral. So do we care about that? Nope. We can ignore that. We can ignore the contribution of NaCl that's present. But what does contribute to the pH? The sodium hydroxide that's present there. So we're going to take this number, all right? So this calculation is no different than chapter 16, right? We have 6 millimoles of sodium hydroxide left over, and that's what's going to contribute to my pH. To calculate pH, you typically do negative log H plus concentration, but the approximation that we use here is that 6 millimoles of sodium hydroxide contributes to the overall OH minus concentration total. All right, so how do we get hydroxide concentration? Is it just 6 millimole? No, we have to divide by the total volume. So 6 millimoles of sodium hydroxide that's left over, I'm going to divide by what number? 90, yes, because we have 40 mils that we're combining with 50 mils. So the total volume here is 90. And so remember, a millimole divided by a milliliter is a molarity. So we don't have to mess around with factors of 1,000. All right, and so you calculate that and you get, after the neutralization, there is 0.0667 molarity sodium hydroxide, and then you just plug that into POH and then get pH. All right, and so does this pH make sense here? A pH of 12, whatever? Yes, because what is left over after this neutralization? Hydroxide. So the solution should be basic. There we go. All right, so we are gonna be using BCA tables again. All right, okay, so let's now extend this to buffers. All right, so in that previous example, we did the neutralization. Our product was a neutral salt, so we didn't have to consider it. So now let's neutralize a weak acid system. Now we do care about the base, the product that is produced when we neutralize it, but it's not too bad because we're just going to insert it into the Henderson-Hasselbalch equation. So let's say we start with 80 mils of HF and we add 50 milliliters of sodium hydroxide. What's the pH? Okay. So this is the second way we can make a buffer. You start with an acid, we neutralize it with strong base, calculate the pH. So the idea here with this partial neutralization of a weak acid with a strong base, we need to do a BCA table first and then use those values into the Henderson-Hasselbalch equation. Because in this case, I don't straight up give you the concentration of the base component of the buffer, I only give you the acid component. So in this case, HF, this is the acid part of the Henderson-Hasselbalch, but sodium hydroxide does not go into the Henderson-Hasselbalch. We have to do some BCA business first. So do you want to work in mole amounts or millimole amounts? Millimole, okay, we're doing millimoles. Okay, how many millimoles of acid are present? So 80 times 0.1, 8 millimoles of acid. And then how many millimoles of base are present, or of sodium hydroxide? What is that? 3? Okay, I trust you. All right, so we need to neutralize this first because this is a strong base. So this is the reaction that's happening. We're taking HF, this is our weak acid, we're using sodium hydroxide, and we're making its conjugate base and water. So see the arrow I have? We haven't seen one of these arrows in a long time. This is a reaction arrow. So we have to do a BCA table. So let's do the BCA. So where do the 8 and the 3 go? In the before line. So 8 millimoles of HF, 3 millimoles of sodium hydroxide, 0, 0 of the other 2. The reaction has to go forward. What's our limiting reactant? NaOH, so -3, -3, +3, +3. So after this neutralization, I have 5 millimoles of HF present. I have 0 millimoles of sodium hydroxide. I have 3 millimoles of NaF, and I have 3 millimoles of water. So let's inspect that after line. What is this? If we have HF, NaF, and water present, what is that? That's a buffer. HF and NaF, it's an acid and its conjugate base. So if it's a buffer, how do I calculate the pH? What did we just learn at the beginning of this thing? Yes, the Henderson-Hasselbalch equation. So these are the numbers that go into the Henderson-Hasselbalch equation. It's not that bad, all right? So inspect the buffer, all right? There's the Ka expression for HF, but because this is a buffer, I can just go ahead and say, okay, pH equals pKa plus log base over acid. What is my base over acid ratio? Look at the after line. It's the after line that goes into that base to acid ratio. So it is what over what? It is 3 over 5. That's it. So putting this all together, HF, there's its Ka value. So I think the pKa is, do I have this? Where is it? 3.18. So putting it all together, the pH is 3.18 plus log 3 over 5. Because there's 3 millimoles of the conjugate base over 5 millimoles of the acid, HF. And so that equals something like 2.96. All right, so see how I didn't put 8 and 3 into the B over A ratio, base over acid ratio. We have to neutralize it first because the base, 3 millimoles, this is of a strong base, not of the conjugate base that's in the buffer system. So you got a BCA first, then put it into the Henderson-Hasselbalch. Okay, the only time we can put it straight into the Henderson-Hasselbalch is if we're given the weak acid and the conjugate base concentrations right from the get-go. But in this case, because we're partially neutralizing it, BCA first, then Henderson-Hasselbalch. All right, let's do another one. Okay, so here, this one's a different one. It's a partial neutralization with a base. How do you neutralize a base? You have to add acid, so HCl. So see how this, we're adding a strong acid, HCl in this case. So base and a strong acid like HCl. I'll just write the pKb here is 4.74 and the pKa of ammonia is 9.26, just off the get-go. All right, so let's calculate the solution when we have 80 milliliters of ammonia and 15 milliliters of HCl. So how many millimoles of ammonia are present? 8. 8 millimoles of ammonia, so NH3. And then how many millimoles of HCl are present? 3. Oh, it's the same numbers. That's boring. 3 millimoles of HCl. Okay, do I put 8 and 3 into the Henderson-Hasselbalch? No, because 3 millimoles is of HCl. HCl doesn't go in there. So we need to neutralize first. BCA first, then Henderson-Hasselbalch. So it's actually the exact same work. BCA, ammonia, there's 8 millimoles. Then there's 3 millimoles of HCl. Nothing of the other two. What's our limiting reactant? HCl, so minus 3. Minus 3, plus 3, plus 3. So after this neutralization, we have 5 millimoles of NH3. We have 0 HCl. And we have 3 millimoles of NH4 plus. And then some water, but who cares? What is that? That's a buffer because we have NH3, which is the base, and then we have ammonium, its conjugate acid. So there's the acid. There's the acid part. All right. So if we have a buffer, how do we calculate the pH? Henderson-Hasselbalch, yes. Do you know the base to acid ratio? Yes, it's what's in the after line. So in this case, it is what? 5 over 3. It's 5 over 3 because we have ammonia, that's our base, and ammonium, that's our acid. So to calculate pH, we do the Henderson-Hasselbalch. pH equals what is it? pKa plus log base over acid. What's my pKa for this system? Is it 4.74? No, that's pKb. So if I just take the negative log of the Kb that's given here, that gives me pKb, but I need to calculate pKa. How is pKa and pKb related? They add up to 14 at 25 degrees Celsius, but that's where we're operating 99% of the time. So I'm actually going to put this 9 number in the equation in order for this all to work out. So pH equals 9.26 plus log, what over what? 5 over 3. 5 over 3, and then there's your answer. Is that too bad? Not that bad. And see how they're all easy numbers? Yeah, they're all easy numbers. Okay, great. All right. Oh, let's play the game. Is it a buffer? This is my favorite game. Is it a buffer? Remember, what do you need in order to have a buffer? You need to have HA and A minus. There's 2 ways to achieve that. The first way is easy, where literally the formulas are HA and like sodium A minus. That's the first way to make a buffer. The second way to make a buffer, this one's a little bit harder, where you could start with HA and add a little bit of strong base to partially neutralize to make A minus. Right? That's how you make a buffer. That's for an acid system, but we can also do it for a base system, where I add the base, all right, and its conjugate acid straight into the solution. Or I could start with the base and add a little bit of strong acid to make in situ, inside the beaker, a little bit of the conjugate acid. So let's play the game. Is it a buffer or not? Okay, the first one, HF and sodium hydroxide. So remember, we have to look for weak components. So HF is what? A acid, it's a weak acid, and sodium hydroxide's a what? Strong base. So would adding that strong base make a buffer solution? Yes, it would. Yes, because that sodium hydroxide would make us F minus in the solution. So it's not explicitly said, but adding a little base will make both of those components of a buffer present. So that first one is a buffer. What about the next one? HF and HCl? No. HCl is a weak acid, but what is, HF is a weak acid, but HCl is a strong acid. So 2 acids? No, that's not going to make a buffer, no. So it's 2 acids. HF and KF. Is that a buffer? Yes, it is, because we have HF and its conjugate base, F minus. There we go. So that's a buffer. So if we're looking at these methods, because I do want you to, like, in your mind, categorize them, to recognize, oh, these are different ways to make a buffer. This first one, this is method 2, where you start with the acid, add a little strong base. This third one is method 1, where we add straight up the acid and its conjugate base. All right, next one. Ammonia and nitric acid. Ammonia's what? A weak base. Nitric acid is a strong acid. So would that make a buffer? Yes, it would. Yes, it would. So what method is that? 1 or 2? Number 2, yes. We're starting with a weak base, adding some strong acid. Okay. Ammonia and, oh, that's the same one. So just ignore that. Okay, next one. Ammonia and ammonium bromide. Yes, it is. Because we have ammonia, that's our base, and ammonium, that's our acid. What method is that? Number 1, where it's just adding straight the base, the acid, bam, Henderson-Hasselbalch. Benzoic acid and sodium benzoate. Yes, it is, because benzoic acid is a acid, it's a weak acid. Sodium benzoate is its anion form. So that is method number 1. Okay. Benzoic acid and potassium hydroxide. Yes, it is, because again, benzoic acid, it's just HA. And we're adding a base. So that would be method number 2. So adding a little bit of strong base or acid to that weak component. Okay, benzoic acid and HCl. Benzoic acid is a acid and HCl is a acid. So would that ever make a buffer? No, 2 acids will never make a buffer. So 2 acids. Okay, all right. Sodium cyanide and HCN. Yes, it is a buffer, yes. NaCN, sodium cyanide, that would be the base component because it's CN minus, and then we have its acid form, HCN. So that would be a buffer. That would be type number 1. Okay, sodium hydroxide and HCN. Yes, because HCN is a weak acid, adding a little bit of strong base will partially neutralize it. HCl and sodium hydroxide. No, yeah, but it's a base and an acid. It's a strong base, strong base, strong acid, and those never make a buffer. Because at the neutralization, at the equivalence point, what's the pH of a strong acid, strong base thing? 7, yes, because all you have is NaCl. All right, NaCl and HCl. Okay, HCl is a strong acid, right? So this might be method number 2, but NaCl is what? It's just a neutral salt. So will that be a buffer? No, it won't. So this is not a buffer. It's literally just salt and acid because NaCl is not a weak acid or base. It's neutral. So we literally have something neutral and something that is acidic. That's just going to be acidic. So that one is also not a buffer. Sodium hydroxide, and then what is that? That's an acid. It's acetic acid. So yes, that is a buffer. Methyl ammonia and methyl ammonium chloride. Don't let that scare you. This is literally no different than NH3, where this CH3 component is essentially equal to an H. So is this a buffer or not? Yes, it is. Yes, because essentially we have NH3, there's our base, and then this is NH4+. There is our conjugate acid. So that is also a buffer. All right, the next one, methyl ammonia and sodium hydroxide. That is not a buffer because methyl ammonia is what? A base, because it sounds like ammonia, right? Ammonia is a base, NH3 is a base. And sodium hydroxide is also a base. So those cannot make a buffer. All right, what is that? Methyl ammonia and HCl. Yes, it can, because that is a base and HCl is a strong acid. So what method, what type is that? It's the second type of buffer. Yes. Okay, last one. Or no, so there's some more. Okay, nitric acid and potassium hydroxide. It's an acid and a base, but it's a strong. So it's strong acid, strong base. So is that a buffer? No. All right. Oh, crap. What is that? It's trimethyl ammonia. See, it's no different than ammonia. It's no different than ammonia, where I just replace a hydrogen with a methyl group. I know, it's real hard to see. So if you squint your eyes and just replace the methyl groups with hydrogens, is that a buffer? Yes, it is. Yes, it is. Because we have NH3 over here, and then we have there's 3 H's there, and there's an H there. That's NH4+. So that is also a buffer. All right, it's my favorite game. Is it a buffer or not? And so understanding, again, there are 2 ways to make a buffer. Either having large amounts of the acid and its conjugate base present, or partially neutralizing weak acid to form your conjugate base, or the base, the weak base equivalent. All right, so that is, that's midterm 2. Oh my gosh, yes, so that's midterm 2, but thankfully the rest of this chapter is titration. So we're gonna inspect the titration curves. So we're still gonna use the concepts and the mathematical formulas, the strategies that we've learned previously, but just in the context of a titration. So this is really calculation review. Understanding what is in my beaker. Is it a buffer system? Is it a salt and a strong acid? That's how we will calculate the pH. Because if we look at this titration curve right now, I promise you, you know how to calculate every single part of this titration curve. You already do, I promise. And so just hold my hand and follow me into the dark. All right, so we are literally not learning anything new. Okay, so let's let the titrations begin. Okay, so what a titration is. You'll do this in lab. You'll do this in lab twice, and by the second time, you'll feel more comfortable with it, where you take a pH probe. So remember in 1210, we did titrations, right? You did titrations, but the point of those titrations were just to find the equivalence point, the end point, to figure out, okay, at what volume of titrant are your moles of acid equal to the moles of base? Basically, we were just trying to figure out, okay, your BCA table, when is acid equal to base? That's it. But in this class, in 1220, we actually care about what is the pH at every single tiny drop of that titration curve. That's what we care about now. And we can actually calculate the pH at every portion of our titration curve. We just need to be really cognizant of what is in my beaker at every single part of the titration curve, and that will tell me what equation to use. So remember, during a titration, this is kind of like method number 2, where we add, we have like a weak acid and we add a strong base. This is very similar to method 2. Okay, we're adding strong base. We just need to know what's in my beaker at every single volume of sodium hydroxide added. So that means we have to start with a BCA table to figure out, okay, what's in my beaker first. Then once I figure out what's in my beaker, that will tell me what calculation to do. So let's say we start with HA is in our flask. So in my flask right here, I have HA. In my volumetric, I have sodium hydroxide. So before the titration starts, you measure out HA into your Erlenmeyer. You calculate, you measure the pH. What's in your beaker? What's in your beaker? Acid, yes. Is that the only thing in your beaker? And water, yes. So HA, your weak acid, is the only thing in your beaker. So that's at the volume of sodium hydroxide is 0. So the only thing in your beaker is HA. How do you calculate the pH of just an HA solution? This is chapter 16. If I told you the HA concentration was 0.100 molarity, how would you calculate the pH? X squared over 0.1 equals Ka, where X squared is what? Or the X component is H plus concentration. That's it. That's chapter 16. That's before the titration starts. Okay, so what if you add a little bit of sodium hydroxide? What if you add a little bit of sodium hydroxide? So we have HA, we have sodium hydroxide, we make sodium, so NaA. So now in our beaker, we have HA and NaA present. What is that? That's a buffer. That's a buffer. How do we calculate the pH of a buffer? Henderson-Hasselbalch equation. Great. All right. So let's look at this titration curve. Where is the equivalence point? At what volume of sodium hydroxide? Yes, right here at 10 milliliters, right there. So if this was 1210, your indicator would go off at like 10 milliliters, all right? So if we're at 8 milliliters, have we reached the equivalence point yet? So what is in your beaker? Still a buffer. You still have HA and NaA. You've only partially neutralized your HA. You haven't completely neutralized it yet. So how do you calculate the pH? Henderson-Hasselbalch, yeah, so buffer, Henderson-Hasselbalch. Okay, what if you add 10 milliliters of your sodium hydroxide? So this is your equivalence point. So at your equivalence point, remember, you start with HA. When moles of acid equal moles of base, you've now converted all the acid to what? NaA. What is NaA? It's a weak base. It's the conjugate base. So we only have NaA in solution now. How do you calculate the pH? It's chapter 16. NaA is what? Base. So can we use Ka? No, we use KB. Yeah, so it's literally X squared over whatever concentration it is equals KB. But X is equal to what in this case? OH minus concentration. All right. All right, so let's say we got a little titration happy and we added an extra 2 milliliters of sodium hydroxide. All right, so we are over here in the titration curve. So we overshot it by a lot. So what's in our beaker now? We actually still have NaA present, but now we have a lot of excess what? Hydroxide present, sodium hydroxide. How would you calculate the pH of that? It's not that bad. We're just going to assume that all of the pH comes from the excess hydroxide concentration, that we can basically ignore any sodium, any of the conjugate base that's present, because it's a weak base. Sodium hydroxide is a strong base, so we're just going to assume that all of this excess hydroxide is what gives us our pH, right? And so those are all the components of a titration curve. The beginning of the titration, before you start, you just have the weak acid. At the equivalence point, you only have your conjugate base. It's become all neutralized. Anywhere in the middle, that's a buffer. And so you use the Henderson-Hasselbalch equation. And after the equivalence point, the pH comes from excess sodium hydroxide. All right, so let's do it. Let's do a titration. All right. So let's do it. Before we begin a titration, you, the chemist, adds 10 milliliters of 0.1 molarity acetic acid. What's the pH? So I like to ask myself, what's in my flask? All I have is acetic acid. So this is just a chapter 16 question. So we are right here on the titration curve. We are trying to predict what that pH is. So we can do our ice table here because HA is the only thing present. So we have 0.1 molarity minus X plus X plus X. So at equilibrium, I mixed up ice and BCA. There we go. At equilibrium, we have 0.1 minus X, X, X of HA, H plus, and A minus. And so we can set up our Ka expression, X squared over 0.1 minus X equals, they give us Ka as 1.8 times 10 to the negative 5. Do you want to do the quadratic? No, I don't either. All right, so this ionizes very little. So it's that minus X in the denominator can go away. Now you can easily calculate the H plus concentration. So do remember X in this case is H plus concentration. So what is this? This is X is equal to 0.00134 molarity. Yes, and so if you plug that into the negative log to calculate pH, that's what you get. Okay, let's check our intuition. Does that pH make sense? Yes, okay, it's an acidic pH. The only thing present is a acid. Good, good. Right, that's chapter 16. So now what happens when we add a little bit of base? All right, so now we still have that 10 mils of acetic acid in the flask, but now we add 2 milliliters of sodium hydroxide. What is the pH? So since this is a make a buffer number 2, all right, we're adding a strong base to a weak acid. We have to BCA first to figure out how much do we neutralize, how much did we neutralize to make our buffer, and then we move on to the Henderson-Hasselbalch. We can't just straight up put those values into the Henderson-Hasselbalch. All right, so do you want to work in mole amounts or millimole amounts? Millimole. All right, so how many millimoles of acetic acid is present? 1. Then how many millimoles of strong base is present? 0.2 of hydroxide. This is what goes into our BCA table. Okay, we have 1 millimole of acid, 0.2 millimoles of hydroxide. So what's our limiting reactant? OH. So after this neutralization reaction, how much HA do I have present? 0.8 and 0.2 hydroxide. Oh, sorry, no, that's not right. Okay, let's actually do the work, Lisa, or you'll be wrong. Okay, plus 0.02, plus 0.02. And so after this neutralization reaction, you only consume some of the HA acid, you only partially neutralize it. We have 0 of the strong base sodium hydroxide left because it completely reacted. We have 0.2 millimoles of the conjugate base, and we have 0.2 of water, but who cares? So it's this after line that matters. 0.8 is HA. 0.2 is A minus. So when we plug these values into the Henderson-Hasselbalch equation, it's pH equals pKa plus log base over acid. What's my base over acid ratio? 0.2 over 0.8. Yes, because A minus, that's the base. HA is the acid. So the pH is equal to 4.74 plus log 0.2 over 0.8. And there we go. BCA first, then Henderson-Hasselbalch. You already know how to do that too. We already did things like that. We already did that. This is type number 2. Okay, let's keep going. All right, chemist adds now 5 milliliters of sodium hydroxide. Oh, so going back to this titration curve, we are estimating what the pH is right there at 2 milliliters of base added. Now we are calculating what is the pH at 5 milliliters of base added. All right, so same thing, BCA. We still started with 1 millimole of HA. That did not change, but now all we're changing is how much base we're adding. How much base is present in that amount of sodium hydroxide? 0.5, yes, so 0.5 millimoles of sodium hydroxide. Okay, you consume everything. And so you have, after this neutralization reaction, you have 0.5 millimoles of HA, and you have 0.5 millimoles of A minus. All right, so what is that? It's what? If we have HA and A minus present in the beaker, what is it? It's a buffer. So what equation do we use? Henderson-Hasselbalch, yay. So pH equals pKa plus log base over acid. What's my base over acid ratio? 0.5 over 0.5 or 1. So in this case, the pH is equal to pKa because it's 1 over 0.5 over 0.5. Right? If we think about this, right, this is our halfway neutralization point, right? That we started with 10 milliliters of the weak acid, and it's the strong base is the same concentration. Our halfway equivalence point is 5 milliliters because our full equivalence point is 10 milliliters, where moles of acid are equal to moles of base. So this is our halfway equivalence point. So 1/2 equivalence point. So we are, and you can kind of tell on this graph here that the halfway equivalence point is where pH equals pKa. Mathematically, it's because you've converted only half of your weak acid to weak base. All right. Okay, so let's do the next one. So this is scenario 3, okay? Where are we on the titration curve? You add 10 milliliters of acetic acid and 10 milliliters of sodium hydroxide. This is your equivalence point. This is where now you've converted all of the weak acid to weak base, or its conjugate base. So we are right here on the titration curve. So how many millimoles of acetic acid and sodium hydroxide are present? 1 each. So let's just kind of prove it to yourself that we've completely neutralized your acid system. So we have 1 millimole of HA, but there's also 1 millimole of sodium hydroxide. What's the limiting reactant? There is none. It completely reacts. So -1, -1, +1, +1. So after neutralization, you have 0 HA, 0 hydroxide, 1 millimole of A minus, and 1 millimole of water, but who cares? What is this? That is a base. It is not a buffer anymore. It's not a buffer because there's no HA left. Okay, so now we only have A minus present. How do you calculate the pH of that? Do we use the Henderson-Hasselbalch equation? No, we have to use the Ka or Kb equation. So which one do we use? Do we use Ka? No, because A minus is the only thing in solution, and this acts like a base. So we need to use Kb instead. We can't use Ka in this case because Ka describes HA acting as an acid. I don't have any HA present, so I use Kb. But the calculation is still the same, right? It's x squared over concentration of A minus. But there's a little subtlety here. Do not just put 0.10, again, molarity. So the initial concentration of acetic acid was 0.1 molarity. We've also diluted this whole thing because we're changing the volume. So we actually need to calculate what is the concentration of A minus. So there's 1 millimole of A minus present over what volume? 10? 20. It's over 20. So the concentration of A minus, once we've done this neutralization, is 1 millimole over 20 milliliters. And this is equal to 0.05 molarity, right? Yeah, that's right. So when we plug this into Kb, it's x squared over 0.05 molarity equals Kb. So this is the one that we're using. And Kb is equal to Kw over Ka. All right, and so Kw is 1 times 10 to the negative 14 over the Ka that's given, 1.8 times 10 to the negative 5. And so when you calculate for x, what is x? What concentration of OH minus? And then you get some number. Did I write it down? Did I write it down? Yes, it is 5.56 times 10 to the negative 10. No, it's not. Where is it? No, it's 5.27 times 10 to the negative 6. There it is. Okay, molarity of hydroxide. Calculate POH, get pH. You know how to do everything on this curve already. Everything. This is a chapter 16 concept. You just need to recognize, okay, do the BCA table first, figure out what's in your afterline, and that tells you what calculation to do. All right, so that's the third scenario. Now the fourth scenario is we get a little excited about our titration and we blow past our equivalence point by 1 milliliter. All right, so at first, when we added 10 milliliters of strong base, we completely neutralized A minus. But if we add an additional 1 milliliter of sodium hydroxide, now sodium hydroxide is in excess. But I'll prove it to you here. All right, so we have 10 milliliters of acetic acid, so that is still 1 millimole of acid. Now we have 11 milliliters of sodium hydroxide, that's 1.1 millimole of hydroxide. Put that into our BCA table. BCA. So 1 millimole of HA, 1.1 millimole of hydroxide. What's limiting me now? The acid. So -1, -1, +1, +1. So after the neutralization, we have 0 millimoles of the weak acid. We have 0.1 millimoles of hydroxide. We have 1 millimole of the weak base, and then 1 millimole of water. Okay, but who cares about that? So let's look at the afterline. How do we calculate the pH of that? A minus is a weak base, and you would think to use Kb, but what else is present? A strong base. So we can actually ignore the weak base in this case. So we're basically making the assumption that the OH is the only thing that contributes to the pH of the solution. We can essentially ignore A minus as the conjugate base's contribution. All right, so the pH here, we need to calculate the concentration of hydroxide ion. So it's 0.1 millimole over what volume? 20 1 milliliters, because we added 10 mils and 11 mils here. So it's over 21, and so yeah, there you go. That's the concentration of hydroxide that's left over. All right, the excess that didn't react to the neutralization, and then you calculate your pH. Right? Does that pH make sense in this context? Yes, we overshot our endpoint. We added way too much base, so our pH is basic. Okay, very good. Let's check the previous ones. I forgot about that. So scenario 3, where we completely neutralized HA to our A minus. A minus is what? A base. So our pH should be basic, is it? Yes, it is. Yes, it is. Okay, good. All right. So you already knew how to do all of those calculations. You just need to know what is in your beaker at what point. Doing the BCA table helps. Oftentimes I like to figure out, okay, where would my equivalence point be? And if the volume of titrant is less than that, I know I have a buffer. If it's more than the equivalence point, then I know I have excess space present. So again, here are the different methods that we used. At the beginning, all right, at 0 milliliters of sodium hydroxide, we only had HA present in our solution. So we just did X squared over HA concentration equals Ka, straight up from chapter 16, all right, where we had just a weak acid present. Then if we had a buffer present, meaning that we partially neutralized our system, we didn't quite get to the equivalence point yet, where we have HA and A minus present, we use the Henderson-Hasselbalch equation, right? So you just need to figure out your base to acid ratio. Then at your equivalence point, when the moles of acid, weak acid, equal your moles of strong base, all you have present is A minus, your weak base, the weak conjugate base. So you do X squared over the concentration of your conjugate base, but now it's equal to Kb in this case, where Kb, your X is equal to OH minus concentration, and then you get your pH and your POH and pH. So again, that's chapter 16. You just have to recognize at the equivalence point, you just have your neutralized salt in that case. And then finally, number 4, this is past your equivalence point, where we assume any of the excess hydroxide goes straight into your POH calculation, but do account for dilution because you're changing the volume every time you add titrant. All right. This stuff is hard. This is hard. All right. Recognizing what's present during a titration is the hardest part. You have all the skills to do the calculations at this point. All right. So there we go. So again, always BCA first, BCA first. And you'll always know to BCA first when you're adding a strong base, typically to a weak acid. And then you Henderson-Hasselbalch, or do whatever you have to in terms of these steps. All right. Okay, so remember I mentioned that the optimal buffer region, right, is where the pH curve is the flattest, that there's a minimal change in pH when you add acid or base. So with that in mind, which of these systems would be best suited to prepare a buffer with a pH of 4? All right, so we want to make a buffer system where it can resist pH change around a pH of 4. So which one of these systems will achieve that? So I give you some pKa values, or sorry, some Ka values. So our strategy here is actually to calculate the pKa's of these systems. All right, so let's calculate the pKa of sodium fluoride is something like 3.20. The Ka of acetic acid is that, so the pKa is 4.74. And of a benzoic acid system, it's 4.10. So which one of those systems should be chosen if we need to, buffer some biological system to a pH of 4? Which one do we want to use? We want to use the benzoic acid system. Because remember, these are the pKa's, and when will a buffer have its pH equal to pKa? when the base to acid ratio is 1, and that is when your buffer is most resistant to pH changes. That's where the curve is the flattest. All right, so that's how we choose. Okay, all right, good. Let's keep going. All right, let's test ourselves again. Is this a buffer? Is this a buffer or not? HCl and sodium hydroxide. Is that a buffer? No. Because it's a strong acid, strong base. What about, what is that? Formic acid and sodium formate? Yes. Okay. Formic acid and HCl? No, because formic acid is a acid and HCl is also an acid, so no. Okay, formic acid and sodium hydroxide? Yes, because formic acid is a acid, a weak acid, and sodium hydroxide is a strong base. Yeah. Pyridine and HCl? Yes, because pyridine is a base and HCl is a acid. Okay, great. All right, so for the ones that are a buffer, would the pH be acidic or basic? So let's look at the ones where they are buffers. Are they acidic or basic? Don't overthink it. Formic acid is a acid, so its pKa is going to be in the acidic region. So that means formic acid is going to be acidic. This buffer is going to be acidic. Think about where the pKa is going to be. All right, what about formic acid and sodium hydroxide? It's the same thing, right? Formic acid still has the same pKa here, so it's going to be acidic. But what about pyridine? It's going to be basic, yes, because pyridine is a base. Typically, we give pKb values. Its pKa is going to be a smaller number, so like to the -11 or something, it's going to be much more basic. All right. Okay, weak base and strong acid titration. It's the same exact thing. It's the same thing, except this time we're going to start with a base. We add HCl. At the equivalence point, we have just the conjugate acid present. All right, so the equivalence point is around where on this? Like around 80 milliliters, all right? Okay, so we start with ammonia in the flask and we add HCl. What is present in my flask at 0 milliliters of HCl? Just ammonia, that's it. So how do you calculate the pH? You use pKb, that's it. So we use Kb, sorry. Kb equals x squared over the initial concentration, whatever. Okay. What about at 20 milliliters of HCl? We only partially neutralize it. So this is a buffer. We have NH3 and NH4 plus present. This is a buffer. So we use the Henderson-Hasselbalch equation. What about at 60 milliliters? Also a buffer. We still have NH3 and ammonium because we have only partially neutralized it. It's still a buffer. What about 80 milliliters? No, it's not a buffer anymore. Now we've completely converted NH3 to what? The NH4 plus. How do you calculate the pH of that? Ka, yeah, so x squared over whatever equals Ka. All right, and then what about if we add 100 milliliters of HCl? We have excess what? H plus, and that's the only thing that goes into the pH. We can ignore any contribution of the conjugate acid that's present also. Okay, so let's do this. Before we begin the titration, so we have 10 mils of 0.2 molarity ammonia in the flask. What is the pH? So that's the only thing in solution. So it's x squared over 0.2. Molarity equals Kb 1.8 times 10 to the -5. That's it. It's just base. That's it. So when we calculate for x, what is the what does x represent? The concentration of OH minus, because we used Kb in this case because it's a base. And so you get some value. Okay, let's write it down. What is it? It is 0.00189. Yes. molarity, and then calculate POH, and then get pH is 11.27. Does that pH make sense? Yes, because ammonia is a base, the pH should be basic. Great. So we are right here on the titration curve before we even started. So we just have HA. All right, so now let's add 6 milliliters of HCl. All right, we need to neutralize it first. So ammonia, how many millimoles of ammonia are present? What is that? 2 millimoles of ammonia, NH3. And then how many millimoles of HCl is this? That is 1.2 millimoles of HCl. All right, I like to be lazy. So essentially the millimole amount of NH3 after neutralization. All right, after neutralization is going to be 2 minus 1.2. So there's going to be 0.8 millimoles of ammonia left. And then the millimoles of ammonium that I produce is going to come straight from the HCl I added. And so it's going to be 1.2 millimoles of HCl. And so I just kind of skipped the steps of doing the BCA table. So again, you're consuming some of your ammonia in the neutralization, and it's becoming HCl. So see how those two numbers add up to how much ammonia we started with, right? So that's just an easier way to get to the Henderson-Hasselbalch equation. So this is wrong. 1.2 millimoles of ammonium. This is our conjugate acid. Okay, so I have ammonia and ammonium present. What is that? That's a buffer. How do you calculate the pH of a buffer? Henderson-Hasselbalch. So pH equals pKa plus log base over acid. So my base over acid ratio is what? 0.8 over 1.2. All right, what's my pKa value? Do I put 4.74 in there? No, that's pKb, so we need to do one tiny step to get to pKa. It's something like 9.26. So pKa in this case is 9.26. So we do have to do a little bit of Ka manipulation here. So log 0.8 over 1.2. And that's how we get the pH. This is no different than before. It's just for a base system. All right. Where am I on the titration curve? 10 mils of that, 10 mils of that. Where am I? I'm at the equivalence point. Yes, this is the equivalence point. I know because the mole amounts are equal. If you calculate it, it's 2 millimoles of each. So what is present at the equivalence point? Is it ammonia? Is there any ammonia left? No. All we have left is ammonium, so NH4. That's all we have left over. And so all of that got converted. During the neutralization. So there's 2 millimoles of that present. I actually want to calculate the concentration. So it's going to be 2 millimoles divided by the total volume of the system. So it's 20 milliliters. And so the concentration of ammonium is 0.10 molarity. All right. And since that is the only thing present in solution, how do I calculate the pH? From Ka. So it's just x squared over the initial concentration of ammonium. So in this case, it's 0.1 equals the Ka value. How do I get the Ka value? From Kw and Kb. So Kw over Kb, that's given here. The values are given right there. And so you can calculate for x, and x in this case is equal to what concentration? H plus, yes, because this is HA or Ka, or this is an acid. And so you get the concentration is something like 7.46 times 10 to the negative 6. And then you calculate the pH. Okay. Ammonium is an acid, so you should be calculating an acidic pH, and that's what we have here. All right, so here's scenario 4. We add additional HCl past the equivalence point. So I like to see, oh, if we look at these volumes here, I added 0.5 milliliter, 0.5 milliliters of HCl past the equivalence point. This is going to be equal to something like oh, my battery's low, 0.5 times 0.2. So there's 0.1 millimole of HCl in excess, because I'm only 0.5 mil past the equivalence point. So to get the H plus concentration, I'm just going to focus on that part. 0.1 millimole of HCl is present over what total volume? 20.5 milliliters. And then that will give me the concentration of H plus total and then the pH. And so here we have an acidic pH because H plus is in excess. All right. So now you know every single part of a titration curve.